Okay, today we're going to be talking about equations for planes, and in particular, a scalar equation for a plane. So as a reminder, the scalar equation for a line was based on the normal, which was a perpendicular line to the line that we're talking about. And we had this expression, ax plus by plus c equals 0, as a scalar equation for the plane. Maybe called it the standard equation of a line. It's also called scalar equation of a line. And the normal, which is the perpendicular line, is line AB. So consider the simple equation y equals 2x. This equation can be written in standard form, such that negative 2x plus y equals 0. And the coefficients of each representation are useful in different ways. So let's just kind of take a minute and review. In the slope y-intercept form, we'll end up with negative a over b x minus c. And then from that form, we can determine that slope is 2 over 1 or negative a over b. The reciprocal of that slope is b over a or negative 1 over 2. And what this means is that the direction vector for this line is that every time x moves 1, y moves 2. So this is a rise of 2 over 1. A perpendicular line will have a negative reciprocal slope, so the direction vector of the reciprocal will be negative 2, 1, or every time x moves negative 2, y is going to move 1. C in both cases is just a useful point that demonstrates the position of the line relative to the origin. So that's how far it has been shifted from 0 up or down. So we're going to use the same idea for a plane. And a normal to a plane is a vector that is perpendicular to all vectors in the plane. And that's pretty handy because we actually know how to find a perpendicular vector to all vectors in the plane using the cross product. So if we're given the normal to a plane and the point on the plane, we can find the scalar equation super easy, just using a general point. So let's find the scalar equation for a plane that has the points a, 1, 2, 2, and the normal n, negative 1, 2, and 6. Okay, so first we're going to just find the vector AQ such that x minus 1, y minus 2, and z minus 2. So this is a general form to get to this point here. And now we're going to use this general point in order to find the scalar equation of the line. So we're going to take AQ and dot it with n, vector n. Okay, so we're going to have vector n is negative 1 times x minus 1 plus 2 y minus 2 plus 6 z minus 2 set it equals 0. Okay, when I work this out, I'm going to have negative x plus 1 plus 2y minus 4 plus 6z minus 12 equals 0. Collect my like terms. And 1 minus 4 minus 12 is negative 15 equals 0. And here is the scalar equation of my plane. Okay, well, let's say that we're not given the normal vector, okay? Oh, and as a reminder, the normal vector is perpendicular, so the dot product of this vector and the normal vector must equal 0. Okay, so let's say we're not given the normal to the plane, so we have to find one. The normal to the plane is perpendicular to all the vectors in that plane, so we're going to use the cross product, so this is what we're going to be doing most often to determine that value. The easiest way to find the normal is to find the cross product of two directional vectors. So let's say we have this vector form of the plane. such that we start at this given point, 1, 2, negative 1. We go in this S direction, 1, 0, 2, and in this T direction, negative 1, 3, and 4. And we go in incremental steps that are real numbers. So this is what we're going to do. First, we're going to identify the direction vectors that define the plane. Well, we're given them in this case. We don't actually need to do anything more than that. Now we're going to find the cross product of these vectors. So in order to do the cross product, I write out both vectors twice. I get rid of these terms on the end. And now I'm going to cross 0 times 4 is 0, minus 3 times 2, which is 6. 2 times 1, which is 2, minus 4 times 1, which is 4. 1 times 3, which is 3, minus negative 1 times 0, which is 0. This gives me the vector negative 6, negative 2, 3. This is the direction vector for the perpendicular to the vector. And I actually made a mistake here, so I just need to go back. This here should have been a negative 2 because I had 2 times negative 1. So this is actually negative 6. Okay, and this is not a unit vector, so I'm going to factor out a negative 3. So I get a unit direction vector of 2, 2, 1, negative 1. Okay, here is my perpendicular vector. So this is what I'm going to be using. Okay, so there's the cross product of the direction vectors. Oh, and I made a unit vector of the cross product. Okay, I'm going to take this cross product unit vector for ABC and the point, so this point that I was given in the beginning, from the vector equation. I'm going to sub it into the general scalar equation and solve for D. Okay, I'm going to do this in a really intentional way, and this is just going to help me remember which is what, which different point is what. So what I'm going to do first, I'm just going to write out what my general form is. Okay, so these A, B, and C come from the normal. Now, it doesn't actually matter because multiplication, it doesn't matter whether or not you do A times X or X times A. But in order to remember that A is actually 2, I want you to be sure that you actually fill in A, B, and C first before you fill in the point. And this will help you remember that these are actually the direction, the normal for your plane, and not just a point, because otherwise you might get confused. Okay, so the point that was given was 1, 2, negative 1. So I'm going to fill that in now, 1, 2, and negative 1. And now I'm just going to multiply this out. I have 2 plus 4 plus 1 plus D equals 0. D must be negative 7. And now I'm going to write the scalar equation of my plane. I'm using my ABC, so 2x plus 2y minus 1z minus 7 equals 0. This is the scalar equation of the plane. Okay, let's try another one. In this example, we're going to find the scalar equation of the plane containing these points, A, B, and C. Okay, so step 1, as a reminder, was to identify the direction vectors that define the plane. In this case, I don't actually have direction vectors. I have points. I have A to B to C. So at first step, I'm going to actually need to find AB and AC. Okay, so let's find direction vector AB. From 3 to negative 1, that's 4. From 2 to 2, that's a 0. From 4 to 5, that's a negative 1. AC from -2 to -1, that's -1. From -3 to 2, that is -5. From 1 to 5, that's from 6 to 5, that is -1. Okay, here's my two direction vectors. I'm going to check to see if any of them can be made into unit vectors, and they cannot, so that's done. Now I am going to find the cross product of these two vectors. So 4, 0, -1, 4, 0, -1, -1, -5, -1. I'm sorry, this last one is a positive one. Okay, cross out my last two terms. 0, take away 5. 1, take away 4. -20, take away 0. Okay, so my final direction vector is -5, -3, -20. Let's again check for a unit vector here. And I can at least get rid of this -1, just makes things a little bit nicer. It doesn't actually change much, but let's get rid of that. Okay, so there's the unit vector, the unit vector of the normal. Okay, step 4, I need to solve for D. So here's the general form. And here's where I want you to follow a procedure a little bit, just so that you don't get confused. So this is my A, B, and C. So I'm going to put those in the A, B, and C spots. I just need to get myself a bit more room here. First, okay, so that's my A, B, and C. Now I'm going to put in a point. It doesn't really matter, but I do like to use A because visually I have thought about how A goes from B and A goes from C. So I'm going to put in A here. You can also just take a minute and try this with the other vectors just to prove that it actually doesn't matter which point you use. Okay, so we've got -5 plus 6 plus 100 plus D equals 0. That must mean that D equals -101. My last step is going to be writing out, the scalar equation of my line with my A, which is 5, my B, which is 3, my D, which is 20, my C, which is 20, my D, which is -101, all equal to 0. Okay, for homework, page 285, 1AC, 256, 7AB, and 9.